Welcome to science class. Today we are going to learn about the properties of stars like the sun. Saying the phrase, stars like the sun, would have gotten you killed only a few hundred years ago. The sun was thought to be completely unique, and other stars, whatever they are, were smaller and worse than our star. Then, thanks to technology, we learned that isn't true. There are billions of stars just like the sun in our own galaxy, and there are millions or billions more that are different. Some brighter, some dimmer, some larger, some smaller, some blue, some red. In the last video, we discussed the Big Bang. Eventually, the universe expanded to the point where ordinary matter as we know it could form. The simplest form of matter, in the form of atoms and elements, is hydrogen. The vast majority of the universe still is hydrogen, followed by helium. Gravity causes the dispersed matter within the universe to collect together. As gravity gathers the material together, it begins to compress and becomes more dense, and it gets hotter. This compression creates a kind of internal pressure, which in turn attracts even more material. From the perspective of curved space-time, pressure is a greater attractive force than gravity when it comes to these large collections of space debris. Eventually, matter collected into enormous regions which grew to become galaxies. Within these galaxies, there are the nebulas, which we have discussed before. Within nebulas, stars are born. Stars are collections of plasma held together by their own gravity. Stars form initially out of hydrogen and helium, but the star converts a lot of those elements into plasma. We will discuss how soon. The other significant thing about stars is that deep in their cores, they combine atomic nuclei together through a process called fusion or nucleosynthesis to form the other elements of the periodic table. There was no nitrogen, carbon, or iron in the early universe. It can only be created in the cores of stars or after a star goes supernova. The iron in the hemoglobin in your blood came from a star. Let's get started. We will be covering the properties of stars in general in this video because stars come in many different forms, but we will use the sun as a model to understand how a star works. The only real difference that distinguishes one star from another is its mass. All stars are made almost entirely of hydrogen. Large, hot, blue stars are simply made of more of it than ours is. However big you think the sun is, it's bigger than that. It has a mass of 2 nonillion kilograms. That's 2 followed by 30 zeros. Around 91% of the mass is hydrogen, and virtually all the rest is helium. For now, we will pretend the sun is made only of hydrogen atoms. So why does the sun look the way it does? Why does it glow? Why is it a sphere? All large objects in space are spheres. This is because gravity acts in all directions, and a sphere is the shape you get when you apply a force equally in all directions. As for the glowy part, that will take a while to explain. Stars like the sun form as hydrogen is compressed to the extreme. The sun is so massive and its gravity is so incredibly strong that at its core, the pressure is 260 billion times greater than atmospheric pressure on Earth. On Earth, atmospheric pressure is about 1 kilogram per centimeter squared, so it's 260 billion kilograms per centimeter squared in the core of the sun. That is, I can't believe I'm about to say this, the equivalent of over 43,000 Great Pyramids pressing on an area this big. When you compress matter to that extreme, really weird things happen. For one, if you compress any material, it heats up. The core of the sun is a mind-boggling 15 million degrees Celsius. At those temperatures and those pressures, matter ceases to behave like it does here on Earth. The matter becomes ionized or enters the plasma state. This means that the electrons are no longer attracted or attached to a nucleus. So the core of the star isn't literally made of hydrogen atoms, but it is made of hydrogen nuclei. Remember, the nucleus is just protons and neutrons. So a nucleus that contains only one proton is considered a hydrogen nucleus. If it contains 1 or 2 neutrons as well, then it goes by deuterium or tritium. A nucleus that contains 2 protons and 2 neutrons is a helium nucleus. This insane amount of compression is partly why the sun is so hot and why it glows, but that's not the entire story. The real explanation behind that is nuclear fusion, which occurs in the core of the sun. The sun has layers, but we are only going to worry about the core of the sun. The core of the sun is about 1/4 its diameter, and it's where nuclear fusion or nucleosynthesis takes place. To fuse means to combine together. And remember, I said in the core of the star, you don't find atoms of hydrogen, but rather nuclei of hydrogen mixed with electrons. Nuclear fusion is the fusion of those nuclei. This can only happen in the cores of stars or in particle accelerators here on Earth, because you need insanely high pressures and temperatures. The pressure and temperature allows the nuclei, which normally repel each other on account of them being positively charged, to combine together. When you combine the nuclei of one element together, it creates different elements. Hydrogen nuclei contain only one proton. Helium nuclei contain 2, lithium 3, oxygen 8. You get the idea. This is how many of the elements on the periodic table form. The sun is basically a helium generator. The core of the sun is not hot or dense enough to create other elements right now. Billions of years from now, the sun will be able to fuse a few heavier elements, but that's for another video. Stars much larger than ours can fuse elements as heavy as iron in their cores. Again, more details in a future video. But for now, we're going to talk about nuclear fusion some more because it explains other properties of stars. Something weird happens during nuclear fusion. A nucleus containing 1 proton and 1 neutron, known as deuterium, combines with a nucleus containing 1 proton and 2 neutrons, known as tritium. And this creates a helium nucleus plus one of the neutrons escapes. If we took the mass of the deuterium and tritium and compared it to the mass of the helium nucleus plus the neutron, we find that the helium nucleus plus the neutron has less mass than what we started with. It's an extremely tiny amount of mass, but it just vanishes. How can this be? What happens is that tiny fraction of mass is converted into energy in the form of heat and light. This is the true reason why stars glow and why they are so hot, because the core of the star is well over 300,000 kilometers across, and the entire core is fusing hydrogen into helium. Every single second, 700 million tons of hydrogen fuses into 650 million tons of helium. Yeah, every single second. And that lost mass becomes heat and light. Einstein's famous equation, E=mc², describes this relationship. E stands for energy, m is mass, and c is the speed of light. So when mass is converted into energy, it does so proportional to the speed of light squared. Atoms are tiny, but the speed of light is huge, and so is the sun. So fusion is capable of giving you a sunburn even though you are 150 million kilometers away. What we know about objects that are hot and create energy is they expand. Stars, like the sun, find a natural balancing point where gravity compresses the hydrogen, but fusion in the core pushes back. This is why stars are defined as celestial objects made of plasma held together by their own gravity. Stars that are much more massive than the sun, in turn, have much stronger gravity, which allows them to compress their hydrogen more efficiently than the sun. For this reason, a star that is 10 times more massive than the sun will be less than 10 times the volume of the sun because it is much more dense. It will be hotter and brighter as well. When you look at stars, even with a telescope, you really don't see much. You can tell that some look bigger, brighter, some are red, some are white, some blink, but that's about it. How can we learn about other stars if they are so far away? It's tricky, but we have found ways. The first big problem deals with distance. Let's say we have a candle and a spotlight. The spotlight is much brighter than the candle when viewed side by side, but a spotlight 5 kilometers away will appear dimmer than a candle right in front of your face. Scientists assumed that stars come in a wide variety of sizes, but the closest stars are a few light years away from us, and many that you can see with the naked eye are thousands or tens of thousands of light years away. An extremely massive and bright star, thousands of light years away, may appear to be just as bright as a much smaller star that is only a few light years away. So how are we supposed to tell how big the stars are, and how does mass affect the properties of stars? The first problem to solve, like I said, is distance. How can you know how far away a star is? One method is to measure parallax, which is the apparent shifting of an object due to the change in position of the observer. Do this right now. Close one eye and point directly at something. Now, don't move your hand, but close your eye and open your other eye. You are no longer pointing to the same spot. That's parallax. The longer your arm, the less dramatic this effect is. Try doing the eye test with your finger right in front of your face versus with your arm extended all the way out. You'll find that when your arm is extended all the way out, the shift is less dramatic. The way we measure parallax with stars is we take a picture of the stars, then 6 months later, when Earth has moved to the opposite side of the sun, we take a picture of the stars again. There will be a tiny shift in position of the close stars compared to the very far away stars. Parallax, though, can only be used for a limited number of stars. The closest stars shift less than 1 arc second, which is 1/3600th of a degree. To find out how far away the really distant stars are, astronomers use Cepheid variable stars. Cepheids are stars that fluctuate in brightness. The fluctuation occurs because the star expands and contracts. Thanks mostly to the work of Henrietta Swan Leavitt, we know that there's a relationship between the periodicity of a Cepheid and its brightness. In general, the longer the periodicity, the brighter the star. And I don't mean the brighter it looks from here, but the brighter it truly is. This is what we call absolute magnitude. The brightest star in the night sky is Sirius. Obviously, you can only see Sirius at night, but in terms of absolute magnitude, Sirius is more than 25 times brighter than the sun. Meaning, if they were side by side, Sirius would totally drown out the brightness of our sun. Understanding the relationship between periodicity and the brightness of Cepheids was so crucial, because now we could compare how bright they appear from Earth, what we call apparent magnitude, and their absolute magnitude. This allowed astronomers to finally be able to tell whether or not a star looked bright because it was very close but relatively small, far away but very large, and so on. Let's clarify with an example. Let's say astronomers observe a Cepheid variable star and take note of its periodicity. The rate at which the star dims and brightens tells the astronomers exactly how bright the star is in absolute terms. But from Earth, we see how bright the star appears due to its distance from us. Do some maths, and you can figure out how far away the star that bright would have to be to appear as dim as it does. In the early 1900s, 2 scientists began working out the relationship between brightness and the temperature of stars. By looking at stars, we could tell which were hotter based on their temperature. Red and orange stars have surface temperatures between 2,500 and 5,000 Kelvin, yellow and white stars between 5 and 10,000, and blue stars up to 30,000 degrees Kelvin. But it was not known how that was related to brightness because until Leavitt worked it out, we didn't know how far away these stars were. Thousands of stars were analyzed and graphed, and this was the result. This is known as the Hertzsprung-Russell diagram, after the 2 scientists who created it. The x-axis of this diagram represents temperature, with the highest temperatures on the left, and the y-axis represents absolute magnitude, or true brightness. What we see is a very strong correlation between temperature and brightness. What this taught us is that although all stars are made almost entirely of hydrogen, the stars that form from much greater amounts of hydrogen compress the hydrogen the most, which causes the highest temperatures in the core, which makes them the brightest stars. Small stars that form from much less hydrogen can't compress as much and aren't as bright. You will notice that there are outliers. We have red giants, supergiants, and white dwarfs. We will discuss the outliers in the next 2 upcoming videos. Again, this diagram was so important because it taught us how mass affects the properties of stars. The more mass, the hotter they burn and the brighter they glow. This also teaches us how stars change over the course of their so-called lifetime. We know that a star has to have a certain mass in order to glow blue, about 9 times greater than the mass of our sun. But a blue star could be 9 times more massive or 20 times more massive. In other words, the surface temperature isn't all that precise by itself. So how can we precisely determine the masses of stars? The best method has come from looking at binary stars. As many as 1/3 of the stars in the Milky Way galaxy are binary, where 2 stars orbit around each other. 2 stars of equal mass will orbit around each other around a barycenter. We learned about these in a previous video, which is in between the stars. When their masses are unequal, the barycenter will tend to be towards the more massive star. However, it's common for binary stars to independently orbit around a barycenter somewhere in between them, like what you see here. We also know of groups of 3, 4, 5, 6, and even more groups of stars that all orbit around each other. So it's not just lone stars and binary stars. That is where we will have to end for now. In the next video, we will discuss the properties and eventual death of low-mass stars. Thanks for watching.